Hi guys, so today I'm going to be talking about titration. And first, let's just review what titration is. So titration is mixing acid and base while measuring pH. So we observe the pH changing by when we mix the acid and base. And basically the benefit of this is that we can add base to an acid, for example, and observe the pH go up. And if we want a pH at a certain point, like let's say maybe we want it at 5 or 8, we can just keep adding base until we get to a pH of 5. And then if we want a pH of 8, just add a little bit more base until we get our pH of 8. And then we can use the solution with the certain pH to do, I don't know, an experiment, make something, whatever chemical applications they're needed for. So now that you kind of understand what titration is, let's try to do a titration problem. So this problem says, calculate the pH of a solution that's 25 mils of 0.1 molarity acetic acid, and it gives the Ka, titrated slowly by 0.087 molarity NaOH at various volumes, and find the equivalence point. So first of all, what you want to do is try to figure out what type of titration this is. That's the first step to a titration problem. There's 3 types of titrations. We have strong acid and strong base titrations, where we mix strong acid and strong base. Then we also have titrations which are weak acid plus strong base, like this one here. NaOH is a strong base and acetic acid is a weak acid. And lastly, we have a strong acid plus a weak base. So in this one here, we will probably have like an acid, a base, and then we'll add some acid to it. In this one, we have an acid, and then we add base to it. Same concept, but kind of like the opposite. So the reason you need to know what type of titration you're doing is because these 2 titrations have something called buffer zones, while the first one does not. Strong acids and strong bases do not have buffer zones. And buffer zones require an equation. You guys might know it by the Henderson Hackawalk. I can't even say it. The Henderson equation. I know it. I like to call it the buffer equation because that's what it's solving for. It's solving for the pH in a buffer zone. So this is the equation. pKa plus log of A minus over HA. So our conjugate base is on top and our acid is on bottom when we solve. So we use this equation for buffers because buffer zones refer to points in your titration where you keep adding base, but your pH is just not changing that much. And that's what a buffer really is. And it requires this equation. So you'll have to use it for the titrations I mentioned here, but you don't use it for every single point. There's 2 points you don't use it at, and that's when you're at 0 mils, you have not added base yet, no base added, as well as we don't use it at the equivalence point, and we don't use it after the equivalence point either. equivalence point and on. These are the 2 points we don't use this equation. The rest of them, you use this equation, okay? For all the rest, you use this equation. So let's go ahead and solve for the pH, keeping in mind that we use this equation. We can't solve for pH like the way we traditionally solve negative log of H plus like we can with these. We have to use this equation unless we're at the points I mentioned down here. Let's just go ahead and solve the first couple. I put black dots on the ones I'm going to be solving today, and I'm going to put the work for the rest kind of like in a PDF because I don't want the video to be long. So let's just go ahead and start with the first one. Okay. So at the first place, you'll notice that we have no base added to our acid yet. So we can actually solve for the pH here without the equation and solve for it the traditional way we know, which is we use the Ka given to us, which is 1.8 times 10 to the negative 5 to find the concentration of acid, right, of H plus. So y'all know that this is the equation for that. Here's the initial concentration of acid, and X is going to represent like how much of the acid dissociates, which we can figure out if we know this initial concentration. So luckily we know that it's 25 mils initially. So we can put oops, sorry, I meant to say molarity goes there, not the volume. We have 0.1 molarity minus X. So we can neglect the X and then check our approximation after. So let's go ahead and solve by neglecting X. So 0.1 X squared equals 1.8 times 10 to the negative 5. And X is going to equal 0.00133. And we check it by putting the 0.00133 over the initial concentration and then multiplying by 100. And our approximation works if it's under 5%. This works because it's 1.33%. So great, we found the X. Also, for those of you who want to use ice tables, since we have 0 mils of base, we just have acetic acid in solution, basically breaking apart, disassociating, losing its H plus and creating A minus. So when it initially we don't have any H plus and A minus, we just have our 0.1, we're going to lose some, and that's going to let us gain the A minus and H plus. And then here at equilibrium, we're going to see our final amounts, 0.1 minus X and X. You know that Ka is products over reactants, so these were our products, these were our reactants. So 1x, 2x, x squared, 0.1 minus X goes down here. So that's just kind of how that works. I'm going to get rid of this stuff and just take the negative log of our X, because our X, as you can see right here from our ice and stuff, is going to be our H plus concentration. And we found our X to be 0.00133, so we can just take the negative log to find pH. So let's just take that, figure that out. So according to calculations I've done, the negative log of 0.00133 equals 2.88. And that's why I have this here, because I did them earlier. So let's just go on and do the next one, because in the next one, we're actually using Henderson equation. So this first one was using methods that you kind of already know how to do. And let's use the Henderson problem now. So now we have 5 moles of base. So in the previous one, we had our acetic acid just dissociating by itself, but it's not by itself anymore. There's NaOH in the solution as well. So we have to take into consideration how they react with each other. The thing about acid-base reactions is you have to know who goes with what. So this is going to go, well, this has the plus, right? And this has the minus. This has the plus and this has the minus. So positive and positive don't go together. Negative and negative don't go together. The opposites go together. These go together to make our salt. These go together to make our water. So we're going to get our salt, also known as our conjugate. And here is water. So salt and water is always the result of these reactions. All right. So now we can do an ice table and figure out what our pH is eventually, but we have to do ice table first. So here's our concentration of acetic acid. The thing is, when we added NaOH, we changed the molarity. So we can't put 0.1 here anymore like we did previously. We have to adjust it for dilution. Because when you add, here's our 25 mils of acid, but when we add NaOH to it, we do something called dilution. So we're adding volume. And now that 0.1, that 0.1 molarity, that was for moles per liter, and the liters have increased. So now it's in more volume. So it's kind of like, there's not less of it, but there's kind of like more volume. So there's more space for it. It's like, it's kind of like less concentrated, if that makes sense. Like if you had sugary water, it tastes really sweet, but you add more water, it tastes less sweet because like you've diluted it. So it tastes like there's less sugar, even though it is the same amount. That's just the concept you have to take account for, because there's less sugar kind of per like area, I guess. Yeah. So let's try to do that. So there's an equation for solving for dilutions. And you're going to have to find the dilutions of both that acid and the base because they're diluting each other. So this is the equation. M1, which is M is molarity and V1 is volume, equals molarity 2, volume 2. So molarity 1 is going to be the molarity of just the acid by itself when we're calculating for the acid. And the volume is going to be the volume of just the acid by itself. Molarity 2 is going to be the molarity of basically the combination of the base and the acid together. So, oh, I'm sorry. I meant to say volume. Okay, 1 second. Let me fix that. So the volume is going to be the volume of the base plus the acid. So we know our acid is 25 mils, and here we're adding 5 mils of the base. So 25 plus 5 equals 30 mils. So we have 30 mils total after we add the base. That's going to allow us to solve for our molarity of acid after we've added base. So according to this equation, let's look for the molarity 2 is going to equal 0.083. So now we write 0.083 here. You notice how it went from 0.1 to 0.083. That makes sense. It's less concentrated now. 0.1 was a higher molarity. So we also have to solve for the dilution of the base because the base was 5 mils. And at 5 mils, it had 0.087 as its molarity. But when we add acid to it, its molarity is going to go down. So let's look at that. Our molarity was first 0.087 for the base. I got that from here. And then its volume was 5 mils. We want to know the molarity after. So we're going to put 30 mils here because 30, as we saw from the last one, was what the combination of 25 plus 5 is, the acid and the base. So according to this, our molarity for the base after dilution is 0.0145. So it went down, which is exactly what we would expect. So now that we have molarities, we can actually try to solve our ice table. So we have 0 of this in the beginning. We're going to find out what it is, but we're going to lose our reactants and create our products. So we're trying to see what the pH is after we add the base. This is initial. So we're just assuming reaction hasn't started, right? But here is after the base has reacted and our pH has changed. So we have 0.083, okay, minus X, and then we have 0.0145 minus X, and then here we just have X, and let me go ahead and get rid of this equation. I'll write it down again later. And here we have X. So now it's like, what's X? So you won't be able to solve this if you don't know what X is. In the other equation where it was 0 mils, it was easy because we had our initial amount. Then we had minus X, and then we had a Ka. We ignored the X, and we were able to solve for X by ignoring this. But the thing is, we're not using the Ka method because as soon as we add base, we're in a buffer zone when it comes to these type of titrations. Only strong acid and strong base titrations don't have buffer zones. Every other titration has a buffer zone, except that 0 and after the equivalence point, and we haven't reached the equivalence point yet. So because we're in a buffer zone, we have to use the Henderson equation. And this, guess I'll write it a little lower. This is the Henderson equation, negative pKa. Oops, there's no negative. I'm sorry for writing the negative. pKa plus log of the conjugate base over the acid concentration. So we can't use this method anymore. It's not going to work. So in order to find the amount of A minus, which is our conjugate here, and in order to find this, our acid after dilution, which is this, we're going to have to know what X is. And the way we know what X is something called the limiting reagent. So make a little bit more room again. Limiting reagent is a simple concept. So when you have a reaction, you have an acid plus a base, or like a bunch of materials, they're reacting with each other. These materials are going to make products. So they're reagents or reactants. So sometimes you'll hear limiting reactants, sometimes you'll hear limiting reagents. And the limiting one is the one that has the smaller, sorry, I'm reading like the smaller molarity. So out of these two, this base has the smaller molarity, so it's our limiting reagent. And that just means that when the base and the acid react with each other, if there was more base, the acid would keep reacting. Because there's only 0.0145 moles per liter of the base, the acid has to stop at 0.0145. So all the base gets used up because it's the limiting reagent and there's excess acid, but all the acid doesn't get used up because it's not the limiting reagent, so it has some left over. So it's kind of like if you have like 5 shirts and 2 pairs of jeans, like your jeans are your limiting reagent for like outfits. I don't know if that makes sense, but you know, just like a different example. Non-chemistry sometimes helps me. So let's get rid of these lines. Okay. So our limiting reagent here, or let's replace our X. Replace all our X's with our limiting reagent. So we're gonna lose 0.0145 molarity of here, and then we're gonna use all our base, and then we're gonna put 0.0145 here and 0.0145 here. So now we can finally solve for our pH. So here's the Henderson equation. pH equals pKa of plus log of A minus over HA. Well, our A minus is our salts, right? This is our conjugate base. If this is a basic salt. And here's our acid. So let's plug these in. So we have 0.0145 up here, and we have 0.083 minus 0.0145 here. Sorry, I couldn't write it all in one line. And we're gonna take, and then we also have here we have the pKa, and anytime you say p in front of something, that just means take the negative log of the Ka. P is short for negative log, basically. So right here, we're gonna put negative log of our Ka, which I'm gonna write it, sorry, it's like this. I'm gonna write 1.8 times 10 to the negative 5. And I got that from here in case you can't read my handwriting. I know it's bad. So for the pH, once we solve, now we're gonna get pH equals 4.06. And that's what it is at 5 mils. So we've done one problem using the Henderson equation. Let's do another one. I'm gonna skip 10 mil, 15 mil. I think that's good practice for, I'm also skipping 20 mils. I think that's good practice for you guys. I'll put like some work, what do you call it, my work in the description. But let's just skip to 25 mils and 30 mils and 40 mils. Can't do that much practice in one thing. So let's do 25 mils. Let's do another dilution. We have to do a different dilution every time because we're adding a different amount of base. So originally, let's do our acids dilution first. Originally, we had 0.1 molarity. This side's always going to stay the same, right? Because originally we have the same amount of acid. Our acid doesn't change, only our base is changing. We had 0.1 times 25, and then we're trying to find the final molarity after base is added. Well, we have 25 mils acid, and for our base, we're gonna have 25 mils this time. So we're gonna have 50 this time. So since there's more base, we expect to see a higher pH, right? So that's kind of ahead of time, but the molarity equals, let me check to see what it equals. It equals 0.05. So that's our molarity now. So it's been pretty diluted. Went from 0.1 to 0.05. So let's do our next molarity. Here we go. So for the base, we have originally 0.087 molarity, and we're adding, the base by itself is 25 mils. Then we want to find the molarity after the base and the acid mix. So we have 50 here for the 25 plus 25. So the molarity of our base is going to equal, let me see what I got, 0.0435. So 0.0435. It's diluted. Okay, now we can go ahead and solve. As you can see here, the NaOH is still our limiting reagent, right? But our acid has come so low, it's been so diluted by base as base goes up, that they're kind of starting to have the same amount of molarity in solution, right? So let's just see what happens. So we're losing X, we're gaining product. So right here, we're gonna have our acid minus what it loses, and then right here we have 0.0435, our base minus what it loses. Here we have our gains, which are our products, our conjugate base, which is the salt, the basic salt, and the water. So basically, our limiting reagent, as you can see, the smaller molarity is still the base. So let's go ahead and replace these guys. So this is an important part. Like if you're stuck, remember, oh yeah, I need to subtract my limiting reagent. So minus 0.0, oh, that's not very neat, right? So minus 0.0435. It looks weird in red, I'm sorry. So minus 0.0435, and then we gain 0.0435. 0.0435 molarity. So now we can finally use the Henderson equation, our buffer equation. So we have pH equals the negative log of our Ka, which is 1.8 times 10 to the negative 5, plus the log of our conjugate base, which is our basic salt, 0.0435 over our acid. So our acid is 0.05 minus 0.0435. So here is just our A minus amount over our HA amount. Okay, so now once we solve for that, we get pH equal to 5.56. Okay, so let's do another one. Get rid of this. So something, I'm already gonna say something weird is gonna happen in this next one. And you'll see why. So we have to start all our problems with dilutions. There's no way you can do this without a dilution. A dilution is like the real molarity. You can't just use the molarity given to you in the question all the time, because if base is added, the molarity has changed. So let's find the one for the acid first. We had 0.1 originally of our molarity in 25 mils. And we want our second molarity after base is added. So our volume is going to be 30 mils base plus 25 mils acid. So it's going to be 55. And our molarity too in this case is going to be for the acid. It's going to be, let's see, 0.045. So now we have 0.045 here for the acid, the acetic acid. Let's solve for the dilution of the base. So the base had 0.087 molarity originally, and its volume was 30 mils by itself. After it gets added to acid, it's going to be 30 plus 25. So it's going to be 55, just like that. And our M2, our molarity after they're together for the base is going to be 0.047. So as you can see here, what happened is the limiting reagent changed. It's no longer the base, it's actually the acid. We've gotten to the point that we've added so much base that we've outdone the acid. So now we're actually going to have a more basic solution, right? Because there's more base. And we judge that based off of molarities, but only after dilution, because dilution gives us the true molarities. So let's see how that affects things. So we're going to lose X. They're going to lose X because they react with each other. So reagents get used and products get formed. So now we have 0.045 minus X, 0.047 minus X. Got our X and X. Let's go ahead and replace our X's with our limiting reagent, which in this case is not the base, it's the acid. And limiting reagent is whatever you have less of. So minus 0.045, minus 0.045, gain 0.045. These are the molarities. So now we don't use the Henderson equation. And the reason we don't use it is because we have no acid, 0. So this is the Henderson equation, pH equals pKa plus log of A minus over HA. Where are we going to put the HA? Down here, if it's 0, it's not going to make sense. You can't divide by 0. And that's why I said at the equivalence point and past the equivalence point, we no longer use the buffer equation. Now, this is not the equivalence point. This is past the equivalence point, because the equivalence point is when the molarities equal each other. These two molarities are a little off. So it shows that we've passed the equivalence point. There's more base than acid here. We've passed the equivalence point. So at some point between 25 and 30 mils, our equivalence point was passed. We're gonna figure that out at the end of this video, what the real equivalence point was. But because we have surpassed the thing that we were titrating our acid, and now we have more of the thing that we were titrating it with. So we have more of the base. So now we're past our equivalence point. So we don't use the Henderson equation anymore. We can just go ahead and use basically, we can just go ahead, 1 second, sorry, and take the negative log of our leftover base, which is right here. Because we're gonna have 0 acid, but we're gonna have 0.002 left over of this base. And because there's no more acid, it's kind of like when we were at 0 mils when there was no base. We just used the Ka to find the H plus. Here we already have the OH amount. So when we put 0.0 and take the negative log of 0.002, we get POH. Then we can find pH by subtracting. So POH, when you take the negative log of it, it equals, when you take the negative log of 0.002, you get 2.7. And if you do 14 minus POH, you get pH. So our pH, if you replace the POH with 2.7, it's going to equal 11.3. So 11.3, as you can see here. So what happened was we ran out of acid because we were past the equivalence point, and that means we don't have to use our buffer equation anymore. So at that point, just look at the amount of base you have left over and take the negative log of it. And I'm sorry, I don't think I wrote negative, but yeah, I took the negative log. So that's all you have to do is like use your traditional method of finding pH. Negative log of either H plus or negative log of OH, and then find the pH by subtracting 14 minus POH. So that just depends on the type of titration you're doing. If you're titrating, like in this situation, we had base left over after equivalence point. But if we were in the other situation where we had a weak base and strong acid titration, then at some point we would have, in the beginning, we'd have more base and then we'd add acid. So at some point past the equivalence point, it would just be acid left over. And then we would look here and do the negative log and everything. So this is just how you do that. So that's what happens past the equivalence point. You don't have to use that buffer equation anymore. So let's just do one more past the equivalence point. Let's find 40 mils and then let's find the equivalence point. So always, okay. So now we have 40 mils. So we need to find our new dilutions. So we have 0.1 times 25 mils. And then our M2 times our volume 2, we need 25 plus 40 mils of base. That's a whole lot. So that's going to be 40, 50, 65. Okay. So our M2 is going to equal 0.038 for acetic acid. Now our NaOH is also diluted. So it starts at 0.087 molarity, and then its starting molarity before acid, its starting volume was 40 before acid is added. Once it's mixed with the acid, it's going to be 65. So our second molarity after they're mixed together for the base is 0.053. So now you can see how the molarities, they're kind of changing. Acid's even going lower. It's being diluted because there's more base added to it, so it's less concentration of acid, but we're adding a lot more base. So it gives the appearance that the base is like more concentrated in the solution now. So here we go. We're going to lose reactants and gain products. We have 0.038 minus x and 0.053 minus x, and then we're going to gain x. Our x is our limiting reagent, which is acid in this case. So 0.038 is our limiting reagent. I'm going to get rid of the x's. All right, 0.038 minus 0.038 minus 0.038, gain 0.038, gain 0.038. These are our molarities. Now we can do our pH calculations by just using the leftover amounts of a base, because there's no more acid, so we don't have to use Henderson-Hackle-Block, because the Henderson equation is for buffers, and buffers are when you have good amounts of acid and base kind of like in equilibrium, and that's what helps control our pH and helps our pH not go crazy. But as you can see, our pH was controlled here. Like our pH wasn't going crazy every time. It was within one difference of the next time. But here, it just went insane, right? It just went crazy. So that was because we passed our equivalence point. Equivalence point is like the feather that kind of breaks the camel's back, you know? So now we're going to see the difference here is equal to 0.0, let's see, 0.015, I think. Yeah, it's 0.015. Let me go ahead and take the negative log of that real quick. Okay. The negative log of 0.015, and keep in mind that this is a base that we're taking the negative log of, so it's going to give us POH. So we get 1.82, and then to find pH, we're going to do 14 minus POH, and 1.82 is our POH. So what we get is 13.18. Oops, 13.18. I wanted to write that in pink. This is our pH for 40 mils. So as you can see, past the equivalence point, we can just let go of that buffer equation. So let's try to find out what our equivalence point even was, because we knew we passed it once we had more base than acid. And let's find when did we pass that point? When did we start getting more base? And there's an easy way to figure that out.